Welcome everyone and thank you for joining us in our expert sessions. These are short webinars that take place every 2 weeks and last no more than 30 minutes and brings you valuable insights from the industry experts. Today's session will be presented by Sonny Solanki, who's Senior Technical Manager at I-Gard. Sonny is an electrical engineering with a Bachelor in Engineering by McMaster University, with 8 years of experience in protection systems and relays. Through his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their designs to enhance personnel and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high-resistance grounded systems, low-resistance grounded systems, hybrid HRG systems, chrome fault and arc flash protection systems, resistor-based solutions, and personal protection products. We are excited to have him here today, and we appreciate your participation. Thank you, Sonny.
Thank you, Andrea, for the introduction. So today's presentation will be on the Canadian Electrical Code 2024 requirements for impedance monitoring and 48-hour fault isolation. And let's begin with what a resistance grounded system is. So a resistance grounding involves adding impedance between the XO point and ground, which allows for the resistor to be in series with the ground fault that would be in the system. In that case, the ground fault current gets limited by this resistor, and this limitation prevents the buildup of sufficient energy for arcing, thereby fostering a safer operational environment. Now, in the Green Book by IEEE, there are the reasons for limiting the current by resistance include the following: reduce burning and melting effects in faulted electrical equipment, such as switchgear, transformers, cables, and rotating machines; to reduce mechanical stresses in circuits and apparatus carrying fault currents; to reduce electrical shock hazards to personnel caused by stray ground fault currents in the ground return path; and most importantly, to reduce the arc blast or flash hazard to personnel who may have accidentally caused or happen to be in close proximity to the ground fault. In addition to that, to reduce the momentary line to voltage dip occasioned by the occurrence and clearing of a ground fault, which is a main issue for ungrounded systems in the case of how they experience transient overvoltages when a fault occurs. In addition to that, it's to secure control of transient overvoltages, similar to the ones we see in ungrounded systems, by placing this resistor in parallel with the capacitance that exists between the conductors and ground. Now, if we size that resistor in accordance to the conductance, to the capacitance in the system, then we can essentially control these transient overvoltages such that we won't have the same situation as we would in an ungrounded system. Now, in NFPA 70E, which is a standard for electrical safety in the workplace, it indicates in Annex O.2.2 that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and enabling achievement of an electrically safe work condition. So of the 9 incident energy reduction methods listed in Annex O.2.3, high resistance grounding is the only one that's reducing the likelihood of exposure by placing this impedance in the ground return path at 10 amps or less on a system that's 5 kV or below. It leaves insufficient fault energy and thereby helps reduce the arc flash hazard level. The only issue with high resistance grounding is that it can't reduce the magnitude for all scenarios, particularly for when there's a phase-to-phase and a phase-to-phase-to-phase failure, in which the resistor at the source gets bypassed because the 2 faulted points would be circulating current between each other, growing to thousands of amps and not being limited by the resistor at the source. In that case, it's likely that your instantaneous function of your breaker is going to detect that high level of current and instantaneously trip that breaker that is affected by ground fault and the phase-to-phase failure. Now, in the National Electrical Code, there's acceptance that impedance grounded systems can be used. It's noted that for line to neutral loads, they cannot be served with a resistance grounded system because of the neutral voltage elevation that occurs during a ground fault scenario for high resistance grounding systems. So it says here that the grounding impedance is selected to limit fault current to a value that is slightly greater than or equal to the capacitive charging current. So that way we can control those over voltages. This system is used where continuity of power is required, so we can continue process in the event of the first phase to ground fault, and only alarm the condition of the first fault without having to trip any circuit breaker. So this is becoming more and more popular in industries which cannot tolerate tripping on first fault. And such applications can include, but not limited to, hospitals, data centers, and wastewater treatment facilities, and oil and gas, I guess mining as well. Now, the alarm allows for the safe and orderly shutdown of a process for which a non-orderly shutdown could introduce additional or increased hazards. So refer to 250.36 if you're from the US side for impedance grounded systems and how you can abide by those requirements. Now in Canada, we have requirements for monitoring the resistor for both open and short circuit conditions. And in this case, we have to make sure that even when there's 0 volts and 0 amps, that we are going to be monitoring the integrity of that resistor between its connection from XO to ground. So for impedance grounded systems, you could find the clauses in section 10 of grounding and bonding, particularly in section 10-302, where it says that you can continue signaling the condition of a ground fault until the condition is corrected. And in table 17, which is a very useful table for consultants, you can see the conditions in which you need to initiate an alarm or de-energize your system based on the type of condition that you're currently experiencing. So in the first column here, it indicates for ground faults in the system. The second column is in relation to when you have a short-circuited NGR and your system becomes solidly grounded. And then the last column here is in relation to when your system loses continuity between the XO point to ground, meaning an open circuit condition. And in that case, your system becomes ungrounded, and it's likely that this is the more dangerous of the two, arguably, because in an ungrounded scenario, your protection schemes downstream may not be suitable for an ungrounded system, since the methodology is different for detecting and locating issues. Now let's take a look at resistor monitoring. Now, at I-Gard, we have our Sigma 3C ground fault protection and resistor path fault monitoring relay. The reason why we chose to go with resistor path fault is because we're monitoring the entire path between the XO point to ground, not just the NGR itself. So that includes the wire, the resistor, and as well as the ground connection. So the Sigma 3C combines ground fault protection and resistor path fault monitoring to safeguard systems from ground faults and open or short circuits in the neutral grounding resistor, or NGR, and its connecting conductor. So it's designed for systems ranging between 480 to 69 kV. It monitors resistances as low as 6 ohms, and it's compatible with HRG systems up to 5 kV and fault currents up to 10 amps, and for LRG systems greater than 5 kV with fault currents that are greater than 10 amps up to 1,000 amps. So we have to look at what brought about the need for resistor monitoring in the first place. Well, in the past, what we used to do is that we used to monitor the current through the neutral to pick up the return path ground fault current that would be flowing through the resistor to be limited. Now, this was a good method up until a certain point where it was realized that the NGR was not even connected to the system. In this case, when the open circuit occurs, we've lost our system ground and our three phases are now floating, and this is an ungrounded system. This zero sequence current sensor here is not able to pick up any ground fault current because of this open circuit condition. In addition to that, when we experience a short circuit scenario, we see that the ground fault current may bypass this CT. So it may either split between this short circuit and the NGR path, or it'll go right through the short circuit and bypass this zero sequence current sensor. So it's not guaranteed that we're going to pick up the fault current in this case. And as a result, our system is now solidly grounded, and we're no longer limiting the probability of an arc flash incident by limiting this fault current to a specific value using that neutral grounding resistor. So in the Canadian Electrical Code, it also states that the integrity of an impedance grounded system shall be monitored and controlled as required by Table 17, which we already went through. And that allowed us to modify our approach in terms of monitoring resistances to include a high frequency AC injection method through our sensing resistor. So we already had the sensing resistor in play to monitor for open circuit, and we were using a known voltage and known current at the neutral to pick up resistance faults. And we were also using a DC based injection method at the time that we were initially just looking for open circuits. But when 2018's Canadian Electrical Code came around, what happened was there was a change in monitoring for both open and short circuit, and we realized that we needed to adjust our methodology from a DC based injection to a high frequency AC based injection. So the idea is that from the relay, a high frequency signal gets injected into the sensing resistor, which takes the path up to the XO point and down through the resistor. The reason why we adjusted from a DC to a high frequency AC is because when we were reaching this point, the XO point with the DC based signal, it was realized that a lot of the signal is leaking out into the system if you have YY connected PTs where the primary is grounded. So because the DC signal sees these inductances as short circuits due to XL equals 2 pi FL, we see that the signal can leak out and create a false realization that they've checked the NGR when they haven't really checked the NGR. Now, with the high frequency AC injection, once we reach this XO point, the high frequency forces this inductance path to be of higher impedance than the NGR because of 2 pi FL. So with F being really high, we now have majority of the signal going down through the NGR to be reconfirmed at the relay. And that's how we were able to do the resistor monitoring aspect. So going back to table 17, the requirements are that we need to alarm and de-energize within 48 hours for when there's a short circuit condition. And when there's an open circuit condition, we either alarm if we can still detect a ground fault in an ungrounded system, or alarm and de-energize the system within 48 hours. So our current relay, the Sigma 3C, has this built-in 48-hour delay so that you don't have to utilize an interposing time delay relay in conjunction with our relay to accommodate this additional 48 hours that the code is allowing for. In terms of impedance grounding system configurations, here it indicates the area where a lot of people are taking advantage of, where this is for high resistance grounding on this particular row. In this case, for ground faults in the system, we alarm and de-energize the system within the time rating of the impedance grounding device. But if the unit is rated for continuous use, then we only alarm the condition of the ground fault without having to de-energize, which allows for process continuity. Now, for systems that are greater than 5 kV or when ground fault is greater than 10 amps, then it indicates for ground fault that we alarm and de-energize the system within the lesser of 48 hours or the time rating of the impedance grounding device. But typically for these higher voltages and current levels, you're going to be dealing with more wattage back at the source when a ground fault occurs. So typically consultants like to use 10-second or 60-second rated resistors and trip on first fault with respect to the coordination of the rest of their relays in their feeders and subfeeds. That allows the ground fault to be basically isolated to the area of where the fault is coming from. So make sure to use a 10-second or 60-second rated resistor rather than a continuous rated resistor if you know that you're going to be tripping on first fault. Now, in terms of the detection method, when we are injecting this high frequency AC signal and we don't experience the voltage drop across the resistor and it gets bypassed through a short circuit, we get our full signal back with just a minor drop across the line. And as a result, we can dictate that we're in a short circuit condition. Now, when this high frequency AC signal is running through the route of being injected to coming back to our relay, and all of a sudden there's an open circuit which doesn't allow it to come back, then we can indicate that we have now experienced a break in our connection with respect to our high frequency AC signal. And in addition to that, if there's a known voltage and current, then we can switch to measurement mode where we use Ohm's law to basically calculate the resistance and compare that to the nameplate resistance of the NGR. If we're below 66% or above 150% of that rating, then we can indicate an NGR fault in that scenario. So high frequency AC signal is the key feature for Sigma 3C that basically differentiates us from the competitors in the market currently using a DC based injection. So it's a 4 kilohertz high frequency AC signal, and when the signal reaches the XO point of the NGR of the transformer, most of the signal flows through the NGR path as the impedance of the phase inductances are much higher than the NGR resistance. In addition to that, we've also included CT monitoring so that the relay can detect if the current transformer is open or shorted, and it provides an alarm to alert users to any issues with the CT. Thank you for joining us in this short webinar. We really appreciate it. And now we'll be going towards the questions to see what is being asked and how I can answer. So starting with Christo Shoot, he says, how is the capacitive charging current determined for new designs as well as for converting existing systems to using a neutral earthing resistor? So for that one, capaciting charging current, the main contributor is typically your cabling leading from the source to the gear and from the gear to the loads. And in that case, you can use your cabling data sheets, your SLD and your cable schedule, as well as your site plan to do rough estimates on how much capacitance the cables are contributing. Once you have that capacitance value, you can convert that to a reactance by doing 1/2 pi FC. And then you can divide by the line to neutral voltage of the system to get your charging current per phase. Once you have this value, you multiply that by 3 because you want the total system charging current coming from all 3 phases. So in this case, that's how it's the best way to do an estimate calculation. And there's also another rule of thumb in relation to kVA or kilowatt values, you can send me a message on this, and I will provide my email so that you can get the information from me on what tables I'm using to calculate charging current. So I'll just write my email here for anyone that wants to reach out to me with information. All right. In CSA, is the maximum line to ground fault current allowed for impedance grounded systems 10 amps or 25 amps? For this question, it really depends on the type of system you're specifying. Usually high resistance grounding is at 10 amps or less. When you get to low resistance grounding, anything higher than 10 amps would be allowed. I think the largest one we done was 1500 amps. So there's no limit on the upper side, but it comes down to your feeder pickup levels on your feeder breakers to determine how high are you going to go on the let through current of the NGR, basically. Should the zero sequence current sensors be installed above the NGR or at the ground side to reduce the voltage the CT would be exposed to under fault conditions, potentially requiring very high dielectric strength? So in this case, if you're using a passive CT, typically a 600 volt CT would be okay. We have seen the drawing done both ways, where people have put it on the line side and then the other side where people have put it on the ground side. It doesn't really matter as much unless you're dealing with a CT with connected in series, basically, with the wire. In that case, then you would have to insulate to the nominal system voltage, and then maybe that would increase costs in that case because you would need additional level of protection. But usually passive window CTs where the voltage is not impacting the CT, that would be the route to take if you want to put it on the neutral path on the line side of the NGR. What is the difference of table 17 in CEC 2021 versus 2024 coming from Shiwu Zhang? I didn't see any difference between 2021 and 2024, but there was a big difference between 2018 and 2021 when table 17 was first introduced. Thank you for the comment, Robert, on the good presentation. Does Sigma 3 has a built-in 48-hour timer? The Sigma 3C does, yes, but the Sigma 3 that came before Sigma 3C, that one does not. But we do have an external relay that does the time delay if you do have a Sigma 3 and you need the 48-hour timer. How do system harmonics affect the NGR monitor? So for harmonics, majority of the harmonics are canceling out as they are going back to the neutral, except for the triplen harmonics, which would be the third harmonic, the ninth harmonic, and so on. So in that case, our unit is looking strictly at the fundamental frequency, which is at 60 Hertz. So we're trying to mitigate the impact of higher frequencies in making sure that our readings are accurate on our CT, which is 60 Hertz rated. For level voltage 15 kV or more, how to limit the fault current and max fault current value? Yunez, what you have to do is you have to do the charging current calculation to determine how much charging current there is in your system. And then you also have to look at your protection scheme and what your ground fault pickup levels are on your feeders and sub feeders so that you know how much let through current that you'd have to accommodate for to make sure that the point of fault can isolate itself without impacting the rest of the system. So for example, if you have an 800 amp LSIG breaker and that G function is acting at 20% of the breaker's rating at 160 amps, you wouldn't select a 100 amp NGR if you know that the ground fault is looking for 160 amps. Otherwise, that G function would never activate. So in that case, you would spec out a 200 amp NGR so that you can get enough fault current discrepancy for that 160 amp G function to initiate. I hope that answers the question. Let me know if you can contact me via email if you have further questions on that. Does your solution detect ground faults in the secondary of VFD, especially for low frequency outputs? What I would say is that we're going to be picking up neutral voltage if there's a fault on the output of the VFD. If usually VFDs are isolated though via their own transformers, if they're higher pulse. So we are mostly picking up through neutral voltage rather than current. When a ground fault, okay, hold on. When a ground fault is detected, is the requirement to notify of a ground fault in lieu of tripping open the upstream protection device. Yes, you have to alarm the condition of the ground fault, whether you're tripping or not. So in the case of high resistance grounding, you may be having process continuity, in which case you would just alarm the ground fault condition. But if you have a low resistance grounding system, then you wouldn't keep that system running. You would alarm the condition of the fault and also trip the upstream protection device. Can diodes be used in the grounding system? And if so, what would be the best way to use it? We use a diode in our sensing resistor, and that's so that the current from faults don't go through our sensing resistor. But to use a diode at the NGR, I don't think that would be recommended. I don't really have the answer for that, but I can reach out to my VP of engineering to see what he has to say about it. Okay. So one question from Raja Assad. So he says we have to disconnect within 48 hours, right? Once we disconnect the fault, we are good to restart the machine, right? Or we have to isolate the machine for 48 hours. Please elaborate. So what our relay does is it has 3 contacts. It has a trip contact, an RPF fault contact, and a ground fault contact. So when a resistor fault occurs, we're going to alarm the condition of the resistor fault through the RP fault contact. And then the timer begins, and after the timer expires or 48-hour elapses, then the trip contact sends a command to the breaker to trip upstream if the fault is not cleared. So in that 48-hour window where you get the first signal that an RP fault is detected, then you have 48 hours to resolve the issue while the system is still running. And if you can't resolve the issue while the system is still running after 48 hours, then the trip signal will send a command to trip open the breaker. For a 4160 volt system, 400 amp NGR, the resistance is 6 ohms, right at your lower limit threshold of the unit. Have you had success or any issues with the monitor? So for the application I was involved in on a switching system, we had 400 amps 10 seconds on 2 transformers at the switch yard. and it is very, very close threshold to be at because the percentage change is so minute when you're dealing with 6 ohms that the unit has to be very, very carefully calibrated to accommodate 6 ohms. Even a small change in resistance can impact the ohmic value, and as a result, that percent change is much easier reached. So what we do with our Sigma 3C is we have a calibration screen, which allows us to get metrics on the conductance in the system. Once we have that, we can determine how we're going to set our open circuit and short circuit thresholds based on our open circuit and short circuit tests that we do to see what the conductance drops to and increases to in both of those tests. Once we have that information, then we set our thresholds to be just within those gaps so that we can still effectively monitor for open and short circuit. We did have initial scenarios where the unit just required calibration. Initially though, it may be going into NGR alarm, but with calibration, we can clear those and still effectively detect open and short. Okay. Now, PGH acknowledgements of attendance comes with email, correct? I believe so, Andrea. Am I right on that one?
Yes, they will receive it tomorrow.
Okay, wonderful. Okay, so from, I hope I'm pronouncing this right, Mr. Lugo or Miss Lugo, it is mandatory to trip resistor failure in 480 volt / 600 volt high impedance systems. Yes. Is there a way to skip this requirement? There are process plants that trip could introduce a safety hazard. So it does mention that the conditions in which you need to provide an automatic alarm and de-energize your system. Some of these process plants may have gotten exceptions from their authority having jurisdiction to justify keeping the system running beyond a 48-hour period for resistor failure. But for these 480, 600 volt high impedance systems, you have to follow code requirement if you're in Canada and trip within 48 hours. So some of the other clients I have decided to use the max threshold of that 48-hour requirement and try their best to figure out a way to solve the issue of the NGR fault within that time frame as part of their standard operating procedure. They will also have operation plan to basically protect the system knowing that their main breaker is going to trip. So that might be something to look into on that front. If not, then you may have to contact the authority having jurisdiction to get an exception with respect to your particular scenario. If we are using inductive load for our high resistance grounding, do we use the same ground fault monitoring relay? If you're referring to a HRG system and you were talking about monitoring the resistor, you can use the same ground fault monitoring relay. If we're talking about individual loads, I would suggest going to our DSP system where you can monitor the resistor as well as monitor the feeder circuits for ground faults so that you can easily locate faults. Why use 200 amp CT on an LRG system limited to 400 amps for 10 seconds? Some consulting engineers are going to be tripping their system upon 20% detection in a 400 amp system. So that would be like about 80 amps. In that case, they may not need the full 400 to 5 CT, since their trip range is 20% of the resistor's rating. Some people use 50%, some people use 25%. That's where the consultants make their decision, and we just accommodate accordingly with our offering. But most typically, if I was using an LRG system for 400 amps 10 seconds, I would probably use a 400 to 5 CT, just so I can get the full usage. So I think that concludes our questions. I hope I took care of everyone in that front. If not, feel free to reach out to me via email. I think Andrea has provided that, and we'll be sure to get back to you as soon as possible. Thank you so much for your attendance.
Thank you, everyone.